Even more mathematical concepts in language of programming? Let's go for it. In our first episode, we saw how a for loop perfectly mirrors mathematical summation. Today, we'll take that idea to the next level with the integral, which you can think of as the ultimate continuous sum. This integral represents the exact area under the curve, y is equal to x squared in this case. To bring this to life in C++, we actually return to the idea of sum. Our code slices the area into thousands of tiny rectangles and sums their areas. This is how the discrete world of code can approximate the continuous world of calculus. The more rectangles we sum, the closer we get to the true answer. Next, let's explore the limit. If you remember, we touched on the abstract concept of infinity. The limit is how we mathematically explore what happens on the journey towards infinity. This famous limit defines the constant e. Our C++ code can reach infinity, but it can take large steps towards it. By calculating the expression for ever-increasing values of n, we can watch the results converge, getting closer and closer to the magical number 2.718 and so on. Remember the factorial function from our last episode? We use it for counting permutations. Let's build on it to solve an even more common problem, counting combinations. This is the binomial coefficient. It tells us how many ways we can choose k items from a set of n items where the order doesn't matter. The formula relies entirely on factorials. Instead of computing factorials directly, we can use an efficient multiplicative formula. This avoids the huge numbers that factorials produce and keeps the calculation practical even for larger inputs. Our C++ code reflects that. We create a function that applies the formula step by step inside a loop, multiplying and dividing as we go. We also use the symmetry rule to minimize the number of iterations. This is a great example of how we can translate mathematical optimizations directly into code. We've previously covered set union and set intersection. Let's add another fundamental operation to our toolkit, set difference. This finds every element that is in set A but not in set B. And just like before, the C++ standard library has a direct and efficient tool for the job, std set difference. Now, for a more nuanced look at the familiar topic, last time we saw subset. Let's examine its close cousin, the proper subset. A proper subset means all of A's elements are in B, and B must be larger. This subtle difference in math requires a subtle change in our C++ logic. We add a check to ensure A's size is strictly less than B's before using std include. We've already seen intersection for just two sets, but what about many sets at once? That's where this symbol and notation comes in. It means the intersection of all the sets from A1 through AN. In other words, the elements common to every set. In C++, we can capture this idea directly. We start with the first set, then repeatedly apply std set intersection with each new set, and with each step, the collection of common elements gets smaller until only the through intersection remains. The code mirrors the math beautifully, a loop that reduces many sets into their shared core. Now for some new concepts. Let's start with the function composition. This means apply function g, then apply function f to the result. This is one of the most natural parallels in all the programming. It's simply nested function calls. F call g for x. It's a literal translation of the math. We call g, and its result become the input for f. Simple, elegant, powerful. Finally, let's explore two key ideas from linear algebra. First, the norm of vector, which is just its length or magnitude. The formula is the Pythagorean theorem, extended to any number of dimensions. The C++ code follows step by step. Loop, square, sum, and take the square root in the end. Next, and the last one, the determinant of a matrix. This is a special number that reveals key properties like whether the matrix is invertible or not. For the 2 times 2 determinant, the code is a simple formula involving the diagonal entries. For larger matrices, like 3 times 3 or beyond, the computation expands into more steps, often broken down into functions for clarity. Still, the principle remains the same. The determinant condenses the structure of a matrix into a single number that carries a lot of meaning. We can talk about it later. So there you have it. We've seen how new ideas in code can be built directly on top of ones we've explored before. From the continuous evolution of a sum into an integral, to using a factorial function to count combinations. The connections run deep. Math gives us the timeless language of logic, and C++ gives us the tools to execute that logic. They aren't just parallel, they are partners. Thanks for watching. If you like what you saw and want to see more in the future, hit the subscribe button. See you next time.